Welcome to the lair of the Batty Boffin.
Hi there Batty fans, time for an introduction to electricity with the Batty Boffin. Now if you're interested in electricity, there's a little experiment that you can do. Pop along to www.battyboffin.co.uk and there's a downloadable experiment. It's number 11 called Vegetricity, where you get to make your own electrical circuits using things like potatoes, Coca-Cola, you. Have a go at that if you fancy. But here is some of the theory behind why it works. Now we're just going to start off with the very basics here of an electric circuit, but before we go on to electricity, let's start off with something you're probably more familiar with, which is water. What I've got here in black is a hose pipe with some water flowing through it. The hose pipe gets narrow at one point, and keeping the water flowing is a pump. Now everybody's pretty happy with how that works really. The pump pushes the water around and it goes round and round. And we have three things involved in it. We have the pressure. That's the pushing force that the pump makes. We have the flow, that's the water going round, and you'd measure that in, I don't know, litres per minute, how much water is going past any one point. We've also got the amount of narrowing down here. Obviously, the more that is narrowed, the harder it is for the water to go past. And if you want the water to keep going at the same rate when it's narrow, you're going to have to put much more pressure through there. On the other hand, if you keep the pressure the same and you have it narrow, then there's going to be much less water going through. And that's how those all relate. People are generally quite happy with that. Now that is a very good analogy for an electrical circuit, which we've got down here. The pump that pushes the water around is replaced by a battery down here, shown by these long and short lines. And that is pushing the electricity around. By convention, this is the positive side and this is the negative side, showing electricity going this way round the circuit. Just a little incidental here. They discovered electricity before they discovered electrons. Electrons are subatomic particles that actually have the electrical charge. And although we call electricity going this way round, from the positive round the circuit and into the negative again, weirdly and inconveniently, electrons actually carry a negative charge, which means that in your piece of wire there, your little electrons that are bobbling around taking the electricity are actually going the other way round because they've got a negative charge. So the electrons are going that away, but we call the electric circuit going that away. We talk about the current flowing this way. So just to confuse you there, it's called the conventional current. This is the way we think of the electricity going round, although actually the electrons are going the opposite way. But that's irrelevant for the moment. So we've got our current going this way round, and we've got this thing down here marked with R that is resisting the flow of the electrons, and that's called a resistor, stunningly. For once it's got a nice sensible name. And that could be something like a light bulb, for example, a little light bulb that will resist the electricity going through it. Or it could be just an element called a resistor that's there just simply to muck things up, basically. So what we have a piece of wire here that replaces our hose pipe, our resistor that replaces our narrow bit of tubing, and our battery that replaces the pump. So here's something for you to do. Talking about the pressure that the pump produces, the flow of water through the pipes, and the narrowing of the tube. That's for water. This is for electricity. We talk about resistance, voltage, and current. Some of those words you may have heard, some you may not, but you should be able to work out which of those is equivalent to which of these. So, time for you to get a pencil and paper, write down those words, and then you're going to pause the video and join them up to which ones are which. So, pause the video and do that now, please. How did you get on with that? We should have that resistance is the equivalent of narrowing. It resists the flow of water or the flow of electricity. So resistance is narrowing. Current, that's quite an easy one because you think of a water current, how as a stream flows, you talk about the current of the water. Well, it's the current of the electricity as well. So current is the flow. Which leaves the one that you might not have heard of, voltage. That is equivalent to the pressure, the pushing force. It's named after an Italian guy called Mr. Volta, who kind of invented it. I think he was the guy who did the things with the frogs' legs and putting electricity through them and making the muscles jump. I think that was him. Anyway, so those are those three major terms. If you just pop and get yourself a custard cream, pop back in a minute while I've wiped this board down, and we're going to talk about some of the units that we use for measuring these. See you in a minute. So here's our diagram again with our battery of cells that's pushing electricity around and our resistor down there that's kind of resisting the flow. And the three things that we need to be able to measure to be able to tell us about this circuit are the voltage, how much that's pushing, the current, how much electricity is flowing, and the resistance, how much that's resisting the flow of electricity. So let's start off by talking about the units that we would use for measuring those. So voltage, very handily, is measured in volts. And the symbol that we use to abbreviate volts is V. You may have seen things like 230 volts marked on the back of things to say that's the voltage it requires, or if you're in America, perhaps things more like 110 volts. That's quite a lot of volts. So whenever you're doing any experiments on electricity, do not use mains electricity. Just don't do it. You want to be using things like this. AA battery, 1.5 volts. Dangerous, much safer. So please never, ever, ever mess around with household electricity. Always use things like little 1.5 volt batteries or little 9 volt batteries. They're the square ones, the rectangular ones. So voltage is measured in volts, easy peasy. Current, unfortunately, is not measured in currents or raisins or sultanas or anything else like that. It's measured in amps, and they're just named after another guy, Mr. Ampere. I think he was a French guy. So we usually abbreviate it to amps, and the abbreviation for that is A. Nice and easy there. Resistance, however, is futile, as I'm sure you know. And that is measured in another unit named after another guy. That was Mr. Volta, that was Mr. Ampere, this is Mr. Ohm. O-H-M is how you spell it, and we do not use the letter O to abbreviate it, because imagine if you had a resistor that was 2 ohms. Well, it looks like 20, doesn't it? So we don't use the letter O shortened for ohms. Well, actually we do, but we just don't use the English O. We use a Greek letter O. Those of you familiar with the Greek alphabet, which I'm sure is everybody, will know that the Greek letter O is what we call omega, or omega, depending on how you pronounce it. And it's written like a little shoulder, a big fat head, and another shoulder there. And you can put a smiley face in if you want to, but don't do that in exams. So that says 2 ohms, and that's just a Greek letter O because you can't use the English letter O. So 2 ohms is how you would write that, and that's the unit for resistance. So there is its abbreviation, the omega, or omega. So those are the units we use for measuring voltage, current and resistance. And the devices we use to tell us how much they are called voltmeters and ammeters, like amp meters but ammeters, and ohmmeters, if you like, ohm meters. And they usually look something like this. Okay, this is my handy dandy little multimeter. Sometimes you hear them called amp, volt, ohm meters, AVOs. So this is an AVO, or a multimeter, and it has a little dial on the front so you can dial up different things, DC volts, milliamps and bits and bobs down there. And we can put them in circuit diagrams using symbols like these. Resistance is drawn slightly different here, but I will just do voltmeters and ammeters in there. That's the symbol. You have the circle with the 2 lines coming out, and those lines just fit in the diagram like this. Ammeters are measuring the flow of the current, so they actually need to be in the current to measure it. So an ammeter would go somewhere like there, somewhere in the main circuit. Voltmeters are wired up differently. This is called being wired up in series. See, you've got a series of things going round that main circuit. Voltmeters are always wired up in parallel, which means that the wires that come out should run parallel to the main circuit, and it's wired up like that. They're always over some kind of component. Here you're measuring the voltage over a resistor there. You could have something else in there. You could have a motor or something like that. So ammeters are wired up in series, and voltmeters are wired up in parallel like that. Let's just give it a go. I'm actually going to put my voltmeter over a battery here to measure the voltage that's coming out of here. So I've got my handy little Avo here, and I'm going to turn it onto the thing that says DC volts 10. I'll show you a close-up of this in a minute. So this is DC volts 10, which means my scale will go from 0 to 10. So 1.5 should fit nicely on there. And then I'm going to hold my two ends. We have red for positive, which goes on the positive end of the battery, and black for negative on the negative end. And again, I'll show you a close-up of this, and yep, there we go. That's showing about 1.5 volts. So brilliant. Here's a close-up of what I just did. So here we're going to use a digital multimeter, or AVO, to measure the voltage of a battery. First of all, we need to switch it onto the right setting. I'm going to use DC volts and the number 10 setting. That means it'll go from 0 to 10 in one sweep. So that should fit 1.5 volts on quite nicely. The red probe and the black probe are for the positive and negative sides. So I'm just going to hold the red one onto the positive side and touch the black one onto the negative side. And you can see the needle swinging across. This is 2 on our setting. So the needle goes to just below the 2, showing about 1.5 volts. It's probably actually showing about 1.8 on here, which means that this is a good battery. Okay, so that's something you can have a go at yourself. Get yourself a little AVO, always switch them off when you've finished, and try measuring the voltage of some of the batteries around your house. See how you get on with those there. So that's about all for today. Come back to the next video and we'll look at putting some other things in our diagrams here, particularly some electric light bulbs, and you can have some simple circuits that you can have a go with. So I'll see you next time, Batty fans.